Hello, class. This is Mr. Hart, and in this podcast, we want to talk about the law of conservation of energy. So, we looked at how we can store energy with different forms of potential energy, like gravitational and chemical and electric. We also talked about kinetic energy, right, when we're actually using that energy to move. But we want to talk about how this energy moves between these two forms. And it turns out that energy is conserved, meaning it cannot be created or destroyed, only transfer between forms. Okay, so that's the law of conservation of energy. So, for example, that boulder that was on top of the hill when we were looking at potential energy. Okay, once it falls off, it's starting to move, right? So now it actually has kinetic energy. So even though it's losing potential energy because it's lowering in height, it's also starting to move faster and faster. So it's gaining kinetic energy. Okay, so no matter what you do, that energy is never created or destroyed. It's just transferred between forms. It moves between different forms of potential, or it moves between different forms of, or between potential and kinetic, or something like that. Okay, but it's never destroyed. It's just always transferred. Okay, we watched this video. It's an MIT demo they did, where they take a ball and they just drop it, and they see how fast it's moving to measure its kinetic energy. And they take it and they swing it down a rope, and they do some different transfers of energy. But no matter what they do, when the ball is at this height, right, when it's this low, it always has the same amount of kinetic energy because it's transferred from gravitational to potential, or sorry, from gravitational to kinetic. So it doesn't matter if it just falls straight down or swings down a rope, or whatever it does, it's always going to have the same amount of kinetic energy because it's not created or destroyed. Okay. So we did a lab in class called the Energy Transfer Lab. It talks about some of these transfers that happen, okay? And it taught about how to do energy transfer paths. So make sure you do that worksheet if you haven't already. But again, just this key idea that energy is never created or destroyed. Okay, so let's look at this problem, for example. Okay, so which roller coaster will not have enough kinetic energy at the bottom of the first hill to carry the car over the second hill? This is going to be A or B or C or D. Okay, and if you think about it, the only one that won't make it over is C, okay, because it has this much potential energy. Okay, it has a certain amount of potential energy because it's at this height, okay? And so the energy might be transferred to bring it down the hill, and down here it may have a lot of kinetic energy, right? It might be moving really fast. But then as it goes back up, it's going to go back to this height, and it has to stop because it can't create energy to get over the hill, okay? That energy is conserved. Once it's at this height, it doesn't have any more energy to go back up. So it doesn't matter if it goes back down and then back up. This is as high as it can go because that's the only amount of energy. So the total energy, no matter what you do, is going to be the same, okay? It can't be transferred or destroyed, okay? All right. And then we watched a video of a bowling ball on a string, okay? A professor lifts a bowling ball up to his face, and he lets the bowling ball kind of swing out on a pendulum and then come back. And it doesn't hit his head because, again, potential energy and kinetic energy, they're always going to be conserved. So if he starts it with that much potential energy, he can't end up with more than that after it swings back, so it doesn't hit him in the face. Okay, and so I don't have the link here, but if you search it, I'm sure you can find it. Very interesting video. Okay, but this is the main thing we want to get to. Mathematically, if we want to look at the law of conservation of energy, this is the idea, is that the energy you start with is going to be the same as the energy you end up with, okay? That energy can't be more or less than what you start with, okay? Now, some people may think, well, if a boulder falls off a cliff, doesn't it stop at the end on the ground? And yeah, that's true, right? You would think the energy it starts with is more than the energy it finishes with, but that energy had to be transferred somewhere. So it's either transferred into heat or into the earth, right, to help move the earth, but the earth's really big, so it's not going to move a lot, okay? The energy always goes somewhere, but in most cases, we're going to assume that it's perfectly conserved between two forms or transfers 100% between two forms, but the main idea, again, the energy you start with has to be the energy you end up with, okay? And this can be very useful, okay? Let's look at why this is. Okay, so here's an example problem. A book falls off a 5-meter tall shelf. How fast is it going when it hits the ground? Okay, now to answer this, Um, you could use kinematics, okay, but it becomes a little tricky to figure out what the velocity is going to be. But it's actually really simple to do with energy, okay? Because if you think about it, that book had some initial energy that started with, and it has some energy it's going to end up with, right? Law of conservation. Okay, the energy has to go somewhere. And at the beginning, the book falls off the 5 meter tall table, or 5 meter tall shelf, I mean. All that energy is potential, right? It's not moving, it's just up at a certain height. But at the end, it's touching the ground basically. It's not, doesn't have any potential energy anymore, but it's moving really fast. So all that energy has been transferred into kinetic energy. Okay, so the potential energy it starts with is going to be the same as the kinetic energy it ends up with. Okay, so if we think about what these were, right, from our previous podcast, potential energy was mgh, and the kinetic energy was 1/2 mv squared. Okay. Now something really cool happens because we have an m on this side and an m on this side, so we can actually cancel those out. Okay, so it doesn't matter how massive the book is to figure out how fast it's going, which is kind of cool. Okay, but now we have gh equals 1/2 v squared. Okay, and now we just solve for v. Okay, so we're going to have to times by 2. Okay, we'll get 2gh equals v squared. And then the last thing we'll need to do is we'll need to square root both sides. So we square root both sides, we get square root 2gh, and that's going to equal v. Okay, so now we got it solved for velocity. Now all we have to do is plug it in. So it's going to be the square root of 2 times 9.8 times 5. And I don't have my calculator on me at the moment, but that's going to be about the square root of approximately 100. Okay. And so that's going to end up being about 10. So V is going to end up being about 10 meters per second. Okay. And there you go. Okay, so just by using this law of conservation of energy, we can figure out how fast this book's going to be falling without knowing anything about its mass or anything else. We just know how tall the shelf is. So just by knowing that one value, we can figure out the velocity at the end. Okay, that's pretty cool. So using law of conservation of energy, we can figure out some really cool problems. Okay, so the key here is to be able to identify where the energy is, though. Okay, so the potential energy was at the beginning, right, because it's 5 meters tall. Kinetic energy is at the end because it's moving towards the ground. Okay, so if you can identify the types of energy, you can do really cool problems. Okay, all right. So let's have you try one on your own. If you're doing this for participation, see if you can figure this one out. Okay, so a boy throws a baseball into the air. If he throws the baseball with a velocity of 8 meters per second, how high does it go? Okay, so again, identify. You have energy initial and energy final. Okay, they have to be equal to each other. Think about it, the energy initial is going to be kinetic energy, right? Because the boy throws the baseball. He already used the energy stored in him to throw the baseball. At the end, it's going to be up high in the air. It's not going to be moving. That's going to be potential energy. Okay, so there's your hint. Start with that. Okay, and see if you can figure out the rest. Okay, and then one more. See if you can figure it out. So you're on a roller coaster. Okay, what is your velocity at the bottom of this roller coaster? So here's your little cart. It rolls down the roller coaster. At the end, how fast are you going if you started 50 meters up in the air? Okay. All right, but that is all we did for that video, or for that week. We also did a lab called Down the Hill Lab, so make sure you go to the website and download that if you haven't done that yet. But hopefully that makes sense. Hopefully you can see that the law of conservation of energy is very useful. But let me know if you have any questions, and thank you for watching.